The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Before we get started, let's do a quick sound check first. If you can hear me, press the little hand button on your screen, please. Good, excellent. And now if you should be able to see the first page of the presentation. Can you press the hand button again there just to make sure everybody can see that? Excellent. Thank you. Okay. Good morning or good afternoon. Actually, I see we have at least one person from Canada. Good evening. Welcome to the monthly GoldSim webinar. My name is Rick Kosick with GoldSim Technology Group, and today we're quite fortunate to have a guest webinar from Zoltan Bothi and Tamas Olasz of WSP, formerly Golder in Hungary. Zoltan is a geologist. He's been with Golder for over 20 years, and he's been using GoldSim for a good part, if not all of that period. I first met him nearly 20 years ago in Budapest. His technical expertise is in post-closure performance assessment of radioactive waste management facilities. And he focuses on integrating site characterization data to develop site scale flow and transport conceptual and mathematical models, both in porous and in fractured media. Tamas is a hydrogeologist. He's been with Golder for about 3 years, and he's been using GoldSim for a couple of years also. His experience is in numerical modeling of groundwater flow, contaminant and heat transport, hydrogeochemistry, and modeling coupled processes related to radioactive waste disposal and remediation of contaminated sites. Today, they will be describing an approach that they've developed for representing complex coupled processes, such as thermal, hydraulic, mechanical, chemical, gaseous, microbiological, in contaminant transport models in GoldSim. They developed this approach as part of the EURAD project, which involved professionals from across Europe investigating safe radioactive waste management. But it's really important to point out, and this will become clear as you see their presentation, that the techniques they're going to discuss are really applicable to any type of complex contaminant transport problem. During the presentation, we encourage you to ask questions. So during the talk, if you have a question, please enter it on the screen in the question section. If it can be answered quickly in writing, Tamas will do so. If not, they will address the question verbally either during the presentation, if it makes sense to do so at that point, or we'll save it to the end. Okay, at this point, I am going to hand things over to Zoltan.
Okay, thanks, Rick. Hello, everyone. Welcome to our presentation. My name is Zoltan Bothi, and on behalf of my co-presentation, Tamas Olasz, and on behalf of the whole model developer team, I would like to welcome you. And just as Rick mentioned, we are pretty sure that what we are going to present here could be applicable in your GoldSim practice, no matter what sort of field of application you are working on. But first, we would like to make a short introduction, but we try to keep it as quick as possible. But this is necessary for you to understand the background or the objective of our model development, so that you can understand why this was developed and why it was developed in a way that we are going to present. So as Rick mentioned, the model that we are presenting right now was carried out, the modeling was carried out within the framework of EURAD, which deals with radioactive waste management issues. And within that, our modeling was carried out within the Do Not work package. And this work package aims at improving coupled THMC modeling approaches to better characterize the behavior of the host rock and preferably the buffer, the bentonite buffer materials. It also deals with reactive transport models in connection with performance assessment tools. And one of the issues that they are focusing on is sensitivity and uncertainty analysis. And all of these issues we try to get within our model. As we understand that some of you may not come from the red waste disposal nuclear field, so let's make a very short introduction so that everybody is on the same page. So if we have some radioactive waste, and we are talking about here about high-level waste, including spent nuclear fuel, then these are hazardous material for the environment, which must be managed somehow. Currently, the only accepted general solution for that is called geological disposal. And that means that we are constructing a mine-like facility deep underground called repository. And within this repository, the waste is disposed of. In our model, we have followed, in general, SKBs and possible so-called KBS freeway disposal concept, which can be seen in this figure. What this concept is about. The main part of it is that we've got these orange parts representing the metal canister within which the fuel rods sit. And we could have some intermediate or high-level waste deposited within these horizontal tunnels. These things, as you can see here, are deep underground. In this case, it's a fractured granitic rock, but it doesn't make too much difference from our perspective right now. What is more important is that the canister here is surrounded by this bentonite buffer, this light brown yellowish thing. And although bentonite, which is a squalene clay, has extremely beneficial properties for red waste disposal, that's why it is used, like very low hydraulic conductivity and high retardation capacity. But on the other hand, it also has a few tricks, as it has a very so not a homogeneous sort of behavior, nonlinear behavior, and to represent it properly, that requires coupled modeling to be used. So our model focuses is what is called the near field. So this part of the whole repository, these shallow vertical shafts and the horizontal tunnels and the rock right next to them. What I would like to emphasize regarding red waste disposal issues, for those of you who are not familiar, I would highlight two things that must be considered. One is the extremely long time scale to be considered in this case, and we are talking about thousands to millions of years. And the other one is the inherent, very significant uncertainty related both parameter values and general processes. These two together, I would conclude, leads us to say that you cannot really aim at predicting system behavior at a very precise level, but you should aim at obtaining a good general understanding of system behavior, system evolution. As we mentioned, we believe that the modeling approaches, and this is very important, that this is an approach that we developed, and we are focusing on the methods and the approaches. So this is not for a single site or a facility, repository that we have developed this model for, but this could be applied in other sort of disposal waste related projects. But also, we believe that these approaches could be applied in other fields of application. Here we list a few of them. I won't go into the list in any detail, but in general, I would say whenever you are dealing with the heterogeneous geology, or you've got a long-spanning program, within which program you are sort of required to update your model with the new information and use top-down modeling approaches, I would say the structure, the general approach presented here could be applicable for your application also. So very briefly, we are going to introduce you to what we mean by coupled modeling. Coupled modeling is when individual physical and chemical processes interact in such a way that the result of one is then sort of impacts some of the other ones. In our case, we've got thermal, hydraulic, mechanical, chemical, gas-related, and even microbiological processes all working together to get the system evolution described. And on top of that, in our model, we also consider heat, some chemical component, and radionuclide transport. So all of this together makes up our modeling environment here. On the right, you can see two figures. The top is for thermal related processes. The lower one is for hydraulic. These are here just for examples, but you could see similar ones later on in the show. These represent how individual processes are linked to other processes. So, for example, for heat, you've got some other processes influencing heat, and also the boundary and initial conditions, geometry, material, and the current state variables also play a part in calculating heat-related processes. On the output, heat-related thermal processes influence some of the other processes here, and also have an impact on transport, change some material properties, and may change some of the state variables. So all of these must be included in our model, and to achieve this, you would need to get an updating procedure which works the same way everywhere in the whole model. And this is the logic that we applied in the model. So here you can see that the state variables like temperature, pressure, and chemical concentration impact material properties. So material properties in the model are derived based on the current values of these state variables. And then in the next step, those individual processes are calculated considering both the current values of state variables and the material properties. And the end of this loop is that these processes, some of them at least, may change some of the state variables. So all this loop gets done within a single time step in a modeling process. One of the specifics of our modeling approach is that although in general GoldSim models are not spatially discretized in a way similar to numerical finite element or finite volume models, we use that here for our purposes because we believe that this is a good way of tackling those problems that we are facing when we are trying to do some coupled modeling. Here on the right, you can see the sketch of our GoldSim model, at least this vertical shaft. In the middle, we've got the waste form with the spent nuclear fuel within it, surrounded by the canister part, and then comes the bentonite buffer. Since this is where the coupled processes mainly take part, these are relatively highly discretized in our system, in our model. And outside, we've got the host rock, which is, in our case, some fractured granitic host rock. And also, we've got the EDZ, which stands for excavation damage zone. So this is granite, in fact, but has some properties which have been changed due to the excavation of this vertical shaft right next to it. What you should understand is that if we have those single elements defined within our model, we would call them spatial volumes or spatial elements. That means the same for us. Each one of those elements represents what is called the representative elementary volume, which has homogeneous inner structure and inner properties. And in the model, we use the same or very similar inner structuring logic, including the mathematics that we apply within each of those spatial volumes. And we use very similar connections between neighboring or contacting elements. From now on, after this brief introduction, we are going to focus on actual GoldSim implementation. So from now on, I'm going to switch back and forth between the PPT presentation and the GoldSim model. So if you miss something in the PPT, don't worry about it, because most probably I'm going to talk about it while showing the GoldSim model. The first trick that we have applied in our modeling approach was that, in fact, when we are talking about the GoldSim model, we are talking about two GoldSim models. That was required because we would need to derive values, initial values, to be used for such GoldSim elements such as previous value or reservoir elements, things like that, which use as GoldSim that's a GoldSim terminology, state variables for initial values. And GoldSim only accepts either numerical values or static expressions. And in our practice, we realized that in some cases, when we would use these expressions and we would consider them static, GoldSim did not allow us to use them. So that's why, as a workaround, we came up with the solution of creating a relatively simple model only for the initialization step. This is a static model, so it only reads data from a database called the initialization database and derives values to be used for the main model, which is the dynamic modeling part. And let me show you how it looks like. So this is the initialization model that I'm showing right now. And what I would like to show you here very quickly is that within the geometry, let's say we've got the DH, the disposal hole related parameters. And if I get into any of those, what you can see is that we've got those data elements. And all of those data elements are connected to this initialization EURAD database. That's an access database, Yucca Mountain type, if you are interested. And from these, we derive a lot of other values which would be used for our purposes in the dynamic model, in the main model then. For the material properties, the same applies here. But what I would like to emphasize here is the usage of a lot of 1D or 2D lookup tables. Once again, these are also connected to this same database, but these are used everywhere in our model because we believe that these fit our purposes of having a relatively proper description of how certain material properties change with different state variables like pressure and temperature. The whole initialization model lives here, the main part at least, within the initial conditions container, which is divided into two parts, the input and the output. Within it, you will see the very same general structure applied twice. First of all, we've got a container for disposal hole, that's the vertical part, and for disposal tunnels, that's for the horizontal part. And if you get into any of those, you can see a lot of containers, and these containers represent individual spatial volumes in our system. So what you can see here is sort of the discretization, the spatial discretization of the system in the model. Right now we are in the input container. So what we will see within each of those containers is just the same. Once again, we've got data elements connected to the same database, but this time these all represent values representative for that very spatial volume that we are dealing with. So buffer 0, 1, 1, whatever it means. This is one element in our model. The same structure can be seen within the output in general. Here we are. But if you get into any of those, oops, that's a bit different. Why? Because we've got this guy sitting on top, driving everything in our model. This is called the spatial code. This is an integer value, but this should be looked at as an index. That defines what sort of spatial volume we are talking about here in this case. So we would recommend that these values for the spatial code should not be just sequential integer values, but rather this should be sort of understandable things that you as the modeler can understand what sort of the part of the system it does represent. Why we use this? Well, we've got a lot of selector elements here, and all of these selector elements are just conditioned on the value of the spatial code. And based on these conditions, one is selected, and these are the ones that were done during the input part of the model. So this is how database data become individual values representative for any given part of our model. And this part of this, the lower part where you get a lot of expressions, these represent how we derive values that will be applied in the dynamic model. And all of these are collected within this Excel connection spreadsheet element. And all of them are exported in an Excel. And then in the next step, we are importing that Excel into a second database, Access database. And this database will be used for the dynamic model. So let's move on to the main model. That's where we are going to focus our attention to from now on. Here you can see that we've got the database once again, but here you can see the very same structure, no surprises there. But here what we've got is that the ones without background all are connected to that database, which is called the EURAD main database. This contains data derived from the initialization step model. These very few data elements, they are connected to the initialization database. And we are going to focus our attention onto the near field. This is where everything happens here at this vertical shaft. for the spent nuclear fuel. So let's get into this. Once again, we've got a picture of a sketch of the system. And since we've got so many spatial discretization in our model, we cannot make it look really nice. Sorry for that. But all of these containers on the right, and there are a few more, all of them represent a single spatial volume. The ones at the top represent these guys over the canister. These guys all sit right at the same level as the waste. And then we've got this lower part representing the lower spatial volumes. And we have just arrived to one of the most important things in our model, and that's about cloned localized containers. We use them a lot. Everywhere we use them. Why? Because cloning whole containers clones the entire structure within them, and that makes it easy to deploy the same logic, the same structure everywhere. So if once again, if I go back to the main model and get into any one of those, I would see the very same structure within each and every one of them. And this is the part that you should understand really well to understand the whole modeling approach that we have developed. That describes how a single spatial volume and the processes within it are calculated in the model. We've got all the individual processes here, but we also have some other containers. Let's start with this one, outside connection, just to show you a single thing. Yes, spatial code, the same integer value that we used for the initialization phase model also can be found here, represents the same thing, of course. And this drives the whole thing. This drives it the same way. We've got a lot of selector elements conditioned on the value of the spatial code. And these are connected to the database element, which are, of course, connected to the initialization derived data. So this is how we get from site characterization data through the database, the initialization database, into the initialization step model, derive some data that we would need and apply in our main model, export it in Excel, import it into another database, import those database data into data within the main model, and then we use this logic here to derive what is representative for this very spatial volume. The same goes for geometry, and the same goes for material properties also. Yes, one more thing that I would like to talk about, and I'm not quite sure how familiar you are all with cloning, but what I would like to show here is that if I go just one up, you can see that I mentioned that all of these containers are clones, or at least used to be clones, where clones are shown with this small icon on the top right corner. And as you can see here, none of them are clones anymore. We must free clone them to use them to describe different parts of the system. So these are not clones anymore, but within it, you can see most of the guys, the containers, and all the inner structure within it still are clones. There are two exceptions. One is the outside connection. Why? Simply, this is where the spatial code, which is for the individual spatial volume, lives. And we've got a lot of other things going around. We are going to talk about it later on. And the transport is also free cloned only to make sure that the mixing cell element within it is also free cloned. We are going to talk about it in more detail later on. So this whole structure enables us to provide a very simple way of deploying the same logic, and still enables us also to describe spatial heterogeneity within our system. But to achieve this, you have to follow the cloning procedure step by step. So you start by developing individual modules for the processes. When you think that these guys are working properly, then you can combine them into a single container. Of course, you should make the links between them right at that step. And when you are ready developing this single container, which would represent one spatial volume in your system, then you start cloning it a lot of times. That's the easy part. And then when it is all done, you should first of all free clone them at the highest level, and then free clone a single container. We would recommend using a single container. The one we use is the outside connection container in that case, within which lives your spatial volume index value. And this is where you would define flows and fluxes, so the links between spatial volumes. And you should also free clone the transport and within it the mixing cell. So from now on, let's move on and talk about individual processes. Let's start with the thermal process. So in the model, heat is considered as a special species element because temperature is defined as heat concentration. So for that to work properly in the model, once again, let me show it. Within the transport, there is the species element, and the species element lists heat as a species of this vector. And since this is used here, you can use it very similarly to any chemical component you may use for your contaminant transport purposes. So advection, diffusion, partitioning, all of those things can be defined for it. For that, we were following the methods described within the contaminant transport module guide. So if you need help, let's look it up there. But what is our own development is how heat is also contributing in the model and calculated as a daughter product of some radionuclides. And for that to work properly, what you would need is to describe it within the thermal part. You've got this heat stoichiometry called element. This part represents the energy emitted by the decay of that radionuclide, but you would also need some conversion factors to be applicable. And if you do this properly, then you can calculate the heat pulse right from the inventory defined in your system. So this is not an external sort of boundary condition for your modeling purpose, but this is calculated right within your model. And as I mentioned, heat is, or temperature is defined as heat concentration. So we can calculate temperature by simply linking it to the concentration in water, the heat concentration in water. and we can come up with a water temperature. Here you can see that we have calculated gas and solid temperatures also. If partitioning is absolutely perfect within the model, these should all provide the very same numerical values, but just to make sure that we are not mixing things up, we are always using the water temperature as a state variable in our model. The next part that we are going to talk about is hydraulics. And for that, we developed an unsaturated Darcy flow based modeling approach within GoldSim. And I think that's a very good step forward, because generally you would have some groundwater flow model in the background and use the results coming out of it and apply it within your GoldSim model to run your contaminant transport model. But this may lead to some inner contradiction between the assumptions used by the flow model and your transport model in GoldSim. If the whole hydraulics is implied within the GoldSim model, then no such issue can occur. So for that, we have derived the hydraulic model part, where we would use a pool element, which we call water volume. This keeps tracks of the water volume in the spatial volume that we are in. And for that to work, you would need to define some inflows and some outflows. And here I would like to emphasize that water volume may change not only due to hydraulics, so actual flow of water in and out of this part of the system, but also some of the chemical processes may also either consume or produce water, and these should be all considered in your model. For that, we applied a sort of preferential calculation logic, and that means that from top to bottom, the different processes are considered here for a calculation. And as we move downwards or later on in this logic, only the available water remaining after the previous ones can be used for the next calculation. And one other thing I would like to show you is that for the unsaturated water flow, of course, you would need to keep track of the current water saturation, and then you can apply this to calculate such things as capillary pressure and water heads in your system. And also you would use this to calculate relative permeability and permeability. So changes in water saturation changes your material properties. Regarding geomechanical part of the model, currently we have only included the bentonite swelling. But this is the main part we are focusing on. So this is the one that that really is important for the rad waste disposal system. For those of you who are once again unfamiliar with this issue, bentonite or montmorillonite is a swelling clay. As it hydrates, it swells, its volumes becomes higher, but also the hydrated water it takes up is no longer available for transport processes. It is not a free water which can flow from this part or out of it. So for that to work in our model, what we used is and I have to go to the material properties and into the bentonite properties. Once again, we use a pool element to keep track of what we call the bond porosity of the bentonite. This describes the hydrated water field porosity. And we also have an effective or free porosity, and some of this guy can be filled with free moving water. And for the bentonite swelling, we are also considering local geochemical conditions, and also we use elitization as a process which may change how well the buffer can swell. Okay, let's move on to the chemical calculations, and this part is possibly the most complex of our modeling approach. We developed a hybrid equilibrium-kinetic modeling approach for that, and once again I would rather show it within GoldSim. So within the chemical part, first of all, let's start with concentrations, and let me show you that, of course, all of the chemical components in the system are defined as species. So all of them, which are handpicked by us based on what we may think are the most important reactions and consequently phases, chemical phases, components that we should consider. These are all defined as species elements. And if they are such, then we can come up with their chemical concentration or chemical mass within this spatial volume. And from that, we can calculate their molality, ionic strength, and in the end, their activity. And why we would need that? Because generally, geochemical modeling uses activities rather than mass concentrations. So we can use these to come up with those values and to describe our rates of change for the chemical part. For that, let me show you first the equilibrium constants. And here what you can see is a list of our reactions that we are considering. And let me show you that we've got reaction A, whatever that represents, but we have, in fact, left to right, and here you cannot see it, but we've got also right to left part of that same reaction. And these are combined here. So if we go into this guy and list all the equilibrium constants, you can see reaction A from left to right, reaction A right to left, and so on, all these guys. And why we would need these? Because in our model, actually, even equilibrium processes are modeled as chemical reaction rates. And to derive the proper rates, we would need those. And these are conditioned on what is possible, what sort of chemical reactions are currently possible. And these are all calculated within this part. So reaction possible, it lists all the reactants regarding certain individual reactions, because we would need a certain amount of reactants for a certain reaction to be possible. And the other thing is whether we are in equilibrium, and in our case we are not just talking about a single numerical value, a deterministic value, but we are talking about a small range within which we consider things being in equilibrium. And we assume that the further away you are from equilibrium, the higher reaction rates may apply. So from all of these, we come up with reaction rates for individual reactions. And the other thing that I would like to show you is within the equilibrium, but within the stoichiometry part. And here we've got two data elements with the same internal structure. They are both matrices, where you can have the chemical components as species elements in the rows, and you've got vertical columns representing individual reactions. For the stoichiometry basic matrix, you can see that these are the general stoichiometry values that you would use. But for the stoichiometry current element, these are replaced by some very complex calculations by one, because this is how we can describe the current conditions and what is possible and how much of that material gets into the chemical reactions. Some of the chemical reactions like elitization and metal corrosion are considered to be kinetically limited in our model. Let's move on to gas-related processes. Here, the main thing that I would like to emphasize is that in our model, we've got several gas phases, and all of these gas phases can be either consumed or produced by some chemical and microbiological processes. And in the model, for the gas flow, that's very similar to the one we presented for the hydraulics, so for the water part. But what I would like to show rather is within the material properties and for the gas properties here, we keep track of all the fractions of individual gas phases. Why? Because we derive the gas mixture properties based on those fractions and the individual gas phase related property. So this gives us a gas mixture which has material properties changing with time, changing according to its gas phases and their fractioning. One more thing that I would like to underline here is that we are using the whole gas mixture as a single unit flowing from one spatial volume to the neighboring ones. But since these are all chemical elements in our model, these can be diffused to neighboring parts individually. So yeah, let's move on because time is short, unfortunately. The last of the processes, individual processes that I'm going to talk about is microbiological processes. Since in our application, rod waste disposal for high-level waste, this is possibly the least important. We used a very simplified model, which is based on monokinetics, but we also consider temperature as the current condition, which drives the growth rate and the decay rate of the biomass. And due to these productions and decay, some of them are also generating gas, as mentioned earlier. And we have arrived at the transport process part. And once again, I would go back to GoldSim and show you there. So within the transport container, what we've got is the single cell, mixing cell element representing this whole spatial volume. And within that, we list both water and gas as fluids. And we also list all of the potential solids, but once again, only one of those solids can be active, and this is conditioned once again based on the spatial code value. Here I would like to show you that for the boundary condition in the mixing cells, we always use initial mass, which represents the total mass for the volume at the time 0, of course. And yes, as I mentioned, this mixing cell is no longer a clone, but all the other transport elements are clones, and therefore, when they link to some other parts of the model, these are always linked to the elements, other GoldSim elements, within this same spatial volume container. So these are, in fact, describing local heterogeneous, not heterogeneous for the whole system, but for that case, it is a single value, but local parameters representative in this case. What I would like to also show is that for linking the mixing cells elements, you have to define flows and fluxes, and you have to define them for both water and gas phases everywhere, for all the neighboring spatial volumes. And this is done actually within the outside connection, the other container which is free of clones. And here you can calculate water outflows. So each of those lines represents our calculation of how much water can flow out of this spatial volume into one single neighboring volume. And this is why I would say that when you are developing your model, you should take care not to use too much spatial discretization, because these last few steps that I mentioned must be done manually after the cloning and free cloning is done, and that takes a lot of effort. And just revisiting that general structure of updating in our system, here only I would like to use, I would emphasize that to avoid recursive loops to appear in our model, we always use previous values for state variables. And let me just show you how it's done. For example, with the material properties and let's say water properties, the water density, let's say, we've got water density as a function of T and P. And as you can see, previous temperature and previous water pressure is applied here in our calculation. And with that, I would like to thank you for your attention. And if you've got some questions, we are open for discussing it in the upcoming Q&A session. And Tamas, I think it's your turn because you were monitoring the questions.
Yes, so we have one question about how do we determine the optimal spatial discretization, and if you use a trial and error process or an external model for calibration. And I think you touched on this after this question was asked. Sorry, but we have currently 45 elements in this disposal hole. That's about high as we would want to go, because otherwise the manual work gets too much. But yes, we have to think about what would be enough elements for you, that it doesn't cause numerical problems, but that is not too much to define everything manually.
Yeah, I would agree with you, Tamas, and I would just like to add that generally, when you are doing GoldSim models, contaminant transport models in GoldSim, you would have possibly up to 10, 20 elements describing your spatial part of the model. I think by discretizing the system into this 45 or whatever number of different elements, we are making a step forward, but I would say that the maximum I would possibly can envision as a maximum would be something like 100, but then you should be well prepared for it, that it would take a lot of time and a lot of effort. So, but yes, since we are talking about rad waste disposal programs, which span decades, possibly, in some cases, you would be required to sort of make updated and more sophisticated models, and for some clients that also means that your spatial discretization should be higher, but yeah, I would not recommend going any further than 100, and that would be the very most.
This is Rick. Zoltan, I thought I'd just make a point. You make an excellent point there about how much spatial discretization, but one thing people who are not involved with radioactive waste management may not realize, but think back to one of the first slides that Zoltan showed was the time frames involved. The amount of uncertainty in these systems is huge, right? If we're modeling processes over a million years, there's lots of uncertainty. So you really do need to take a step back and ask yourself, when you do have when you have coarse discretization, it will introduce some kind of error. The question is, how does it compare to the uncertainty in many of your input parameters? And in fact, just in many of the processes you're trying to simulate.
Yeah, absolutely agree with that. Great point, Rick.
Yeah, and that's all for now. There is no more questions. Make sure to ask away now if you have any more.
All right. Well, if there's no more questions, I'd like to thank Zoltan and Tamas for the presentation, and I would like to thank all of you for attending. Please do not hesitate to send an email to Zoltan if you have other questions about what they've done. It's an impressive model. Obviously, he only had an hour to describe it, so he only could just give an overview. But I'm sure he would be happy to discuss the model in much more detail for those of you who are interested.
Yeah, that's right.
Okay, well, great. Thanks everybody for attending, and have a nice day or evening. Goodbye, everybody.
Thank you. Bye.
Bye.